Good morning. So, welcome back to Introduction to Photonics. So, we had been talking about analyzing light generation and amplification. So, we got to the point of looking at an example case of where we need an optical amplifier. We took the example case for an optical fiber communication system, and we defined this specific gain medium, that is erbium, which is doped in silica, as a possible gain medium to achieve amplification at 1550 nanometers. Why are we picking 1550 nanometers? So, the losses for the fiber will be very low. So, so that is why we are looking at that wavelength, and then we are going around searching for an amplifier that can possibly or compensate for the losses in the optical fiber during propagation. And so, we took the example of an erbium silica fiber amplifier, erbium doped fiber amplifier, in short it is called EDFA, and then we jumped on to understanding this amplification process itself. So, we looked at an elemental gain medium just involving transition between two levels, and for that sort of a medium we found the gain, the expression of the gain is given by exponential of gamma multiplied by the length of the amplifier, where gamma itself is expressed as n into sigma, where n corresponds to the inversion that you can achieve. So, that is essentially the number of excited ions versus the number of ions in the ground state, that is n2 minus n1, and multiplied by sigma, where sigma we define as the transition cross section, and we assumed that the transition cross section is actually equal for both the emission as well as the absorption, right. So, that is how we came up with this common term. We will of course go back and question this, because if you look at the absorption cross section, absorption emission cross section of erbium, you find that when you look at the cross section as a function of wavelength, you find that the absorption cross section, which is given as blue, is different from the emission cross section, which is given in purple. Okay. So, we may have to deal with these terms separately. Okay. So, you have to, instead of mentioning as a common term as sigma, we may have to qualify that as sigma A and sigma E, sigma A corresponding to absorption cross section and sigma E corresponding to emission cross section. Just looking at this, what do you think the relative values of sigma E and sigma A should be if you want to make amplification? Would you get amplification across this entire band that is mentioned? So, we are talking about a band that is in this case represented between 1400 to 1600 nanometers. Do you think it is possible to get amplification across the entire band? So, where do you think you are likely to get amplification? So, you obviously need inversion for getting amplification, but that inversion is also that it's not just the inversion by itself, that inversion is multiplied by the transition cross section, and you want more of emission than absorption if you want to get gain, right. So, you can essentially say this region where the emission is greater than the absorption is likely the region where you can get gain. Okay. If you have a absorption cross section or the probability of absorption more than the probability of emission, then it is going to be very difficult to get gain. Do you understand that? So, we will come back and qualify that, but as of now we assumed that sigma A and sigma E are equal, which is probably happening as far as this graph is concerned for a particular wavelength at maybe around 1530 or so. Okay. So, that is one thing to keep in mind. We will like I said, we will go into a little more detail later in today's lecture. But the other thing I wanted to give you a perspective of is the graph on the left side, which is plotting what it calls as optical density as a function of wavelength. Optical density, you can look upon that as absorption as a function of wavelength. For erbium crystal, erbium doped crystal, the crystal name is that BIAFTB, does not matter what it is, but this is a characteristic absorption spectrum for erbium. And what do you see? You see multiple peaks in that absorption spectrum. So, what does that signify when you see multiple peaks like this in the absorption spectrum? It has multiple energy levels, right. So, it an atom can absorb a photon which has multiple wavelengths, right, and each of those wavelengths that it can absorb corresponds to a particular transition, particular value of delta E, energy difference between the ground state and the excited state. So, all these peaks are saying that I have multiple energy levels. So far we have been just considering 2 energy levels, but in reality you have to consider all these different energy levels when you are trying to find the gain of this amplifier. So, you can essentially achieve an inversion potentially by pumping at any of these wavelengths where there is a peak, because at all these wavelengths you can absorb energy, and that absorption will take the erbium atom from a ground state to a higher energy level, and from one of the higher energy levels you can get emission, and you can probably get stimulated emission also. Okay. So, this is typically the kind of picture that we are going to be looking at. So, we will as we move on in today's lecture and the next, we will start considering 3-level systems, 4-level systems, and so on, and try to find out what are the characteristics of those type of atomic systems. Any questions about this before we move on? So, the emission, it is not given, but you can, so the emission in the 1550 band, which corresponds to this region, is provided, and but you can imagine that wherever there is absorption, there is a possibility of emission also. Okay. So, you can probably make a laser around 972 nanometers or 800 nanometers, or this high peak over there at 519 nanometers, that corresponds to green. So we have made green lasers out of this erbium systems as well, right. So there is a possibility of emission as well, although that's not indicated in this particular picture. Okay. But when we come back to this system, right, and we sort of left off without completing this, because we started with a requirement of 20 dB gain from our amplifier, okay, and so now we can throw in specific numbers and try to see what should be the length of the amplifier that you need to achieve 20 dB gain, okay. So let's go on to substitute some numbers. So let us say we have at lambda equals to 1550 nanometer, let us say you have an emission cross section corresponding to 6.5 multiplied by 10 power minus 25. What are the units of emission cross section? Centimeter square or meter square. In this case, it is actually expressed in meter square, okay. And if we are told that the fiber that we have has a uniform doping level, okay, and that doping density is given by 1 into 10 power 24 per unit volume, okay, 1 into 10 power 24. So just think about these numbers for a second. I mean, the absorption cross section is a fairly small value, right. So you say, okay, that the probability of that happening is very, very small, but then you consider the number density of erbium atoms, it is at such level, you're talking about 10 power 24. So maybe the probability of this absorption or emission event happening is not so bad, right, because the numbers that we are, and the number density of erbium ions that we are looking at is fairly high, okay. So we are also told that 80% of the erbium ions are in excited state, right. So you have somehow managed to pump it externally and maintain 80% of your ions in the excited state, okay. So what is N2 now? Total is 1 into 10 power 24, 80% of that is excited point, so this is going to be 0.8 10 to the power of 24 per meter cube, right. And what is N1? 0.2. If these are the only two states that we are considering, N1 is 0.2. So what is the inversion? Is 0.6 to 10 power 24 meter cube. So you have that many number of sites which are available for stimulated emission, okay. So that inversion, that population inversion is what can give rise to gain, right. So, if this is the case, this implies that gamma at a specific wavelength of 1550, because the transition cross section is given for this wavelength at 1550, gamma is given by n into sigma, right, where n is the inversion and sigma is the transition cross section. So, in this case it is n is 0.6 into 10 power 24, sigma is 6.5 in 10 power minus 25, 0.4, right, 0.4, I will just say it is approximately 0.4, what are the units? Per meter, right. So, the gain that you have available, the gain coefficient I should say that is available is 0.4. What does it have to be multiplied with to get the actual gain? The length of the amplifier, right. So, what we are told is that the gain required is 20 dB, which is a factor of 100, right. So, we can say that 100 equals exponential of 0.4 multiplied by the distance d for the amplifier, or in other words d is going to be given by 1 over 0.4 ln of 100, right, and if you substitute ln of 100 is about 4.56 or something like that. So, if you substitute those numbers, what you will find is it's about 11.5 meters. So, for this case we need a erbium doped silica fiber of length 11.5 meters, okay, to achieve a gain of 20 dB. You understand this? Mind you, one of the assumptions that we have taken as far as this problem is concerned is that, well, of course, that the emission and transition cross sections are equal, right, that is one assumption. We will come back and question that assumption. But the other assumption is that 80% of the erbium ions are in the excited state all across the length of the fiber, right. Only if that is the case, then you can say this. Otherwise, you will have to see what is the inversion at each location, and you know, you have to account the inversion at each location. So, what is the corresponding gain coefficient at each location, and based on that you would have to do that calculation. So, what I am talking about is, if you go back and look at this picture over here, we said both our pump as well as the signal is actually launched from one end of the fiber, okay. So, the pump is actually getting absorbed as it propagates down the fiber, okay. And what can you say about how the pump will get absorbed? What would be the pump power as a function of distance? How would that look like? It will be decreasing and it will be exponentially decreasing, right. So, if I were to be rigorous about this, I would say that, you know, if I launch a certain pump power, it is going to be exponentially decreasing as it propagates down the fiber, and correspondingly the inversion that you get will also be exponentially decreasing. So, the inversion is not uniform in a real case, okay. But for simplicity in our problem, we have assumed that it's uniform, okay. I just wanted to give you that perspective. Our problem says, okay, 80% of the ions are in the excited state all along the length of the gain medium. So, you somehow manage to pump from the side of your fiber and get them all excited, get the erbium excited, which is practically a very challenging thing to do, but for the sake of this question, we have assumed that. Okay, but this is just an illustration to say, if I know that so many ions are excited, then I can actually find out what is my what is the gain of that system. So, when we look at this sort of a system, we see there is only 2 levels, and of course, they have a certain rate at which absorption takes place, certain rate at which stimulation takes place, and we are tracking only the number density, whereas we are assuming that Wi, which is the transition, the stimulated absorption or stimulated emission transition rate is the same, okay. But this, although it helps us in this understanding, this is not a practical case, right, because if you have only 2 energy levels, you have to pump at that wavelength, at a particular wavelength, and you need to extract the signal at the same wavelength, okay. And if the transition cross sections are the same, then you almost have assuming that all your ions are excited, the best case, you have equal population for N2 and N1, because both the transitions are equally probable. It's like tossing a coin, right. So, you will have equal probability for N2 and N1, and in which case, it's not possible to get your gain amplification in a 2-level system, okay. So, you cannot normally have just 2 levels for your amplifier or your laser, okay. So, what you normally have is what we were trying to project in the case of erbium, right. You would have another energy level that is also participating in this in this process. So, you essentially pump to a higher energy level, lose some energy due to non-radiative relaxation, and then you have an inversion built to provide amplification, okay. So, let us look into such a model. Let us evolve from just a 2-level system to a 3-level system, and let us see how things work out in a 3-level system, okay. So, let us just consider a 3-level atomic system, okay, in which you have a ground state, you have an excited state. So, you have your pumping happening, maybe I can use a different color for this. Maybe pumping is happening, let us say at a rate R1, right. So, you have pumping happening at rate R1, it goes to this energy level, and from there let us say it rapidly decays to another energy level. Okay. So, and if you are told that suppose this is N1, this is N2 and this is N3. If you have a condition that N3 corresponds to a short lifetime, very short lifetime. This is the case of erbium also, right. So, erbium you have this N2 level which has a long lifetime. N2 for erbium in silica could be in the order of 10 milliseconds, right, whereas N3 the energy level corresponding to that N3, that is actually in the order of a fraction of a millisecond. Okay, so it's in the order of 100 microsecond. So if you have this condition, what you can say is, if I say this is happening at R2, you can say that whatever rate, this would imply that whatever rate I am pumping, I am rapidly giving up that energy through non-radiative relaxation, so that R2, which corresponds to the rate at which that relaxation happens, is almost as rapid. Okay, if you have a very short lifetime for that excited state, right, and so then you can represent that entire thing with a common rate R. Okay, and once you relax to that energy level E2, where the number density can be represented as N2, especially if you have a very long lifetime for this energy level, you can say that basically all the erbium atoms, or all the atoms in this particular system are sitting in this higher energy level, and from there there are different events that are possible. One is that it can actually do a spontaneous emission, right. So, maybe I did the squiggly line for non-radiative relaxation, but spontaneous emission is actually a radiative relaxation. So, you can either have spontaneous emission, and let us say that is happening with the time tau to 1 with a rate it's defined by 1 over tau to 1. You can have spontaneous emission, or you could have stimulated emission, right. You could have stimulated emission, you could also have stimulated absorption. Okay. Let us consider this rate to be Wi. Okay, that's a common rate at which both the absorption and emission can happen between those two energy levels. Okay. Now, to find out how the what we are interested in is how is the inversion changing as a function of certainly pump power, but also as a function of the incoming signal photons, right. This is the signal photons that you want to amplify in this medium. Okay. So, you are trying to multiply these signal photons, but we are interested in the inversion or through that the gain that is available from the system for different levels of signal photon density. Okay, so that is what we are trying to achieve. So, to do that, you have to write what is called the rate equation. So, you have to track all these rates. Okay. So, let's go ahead and try to write the rate equation for a system like this. And let's say we are looking at the rate equation at steady state. Okay. So, we are not looking at a transient phenomena, right. We have turned on the pump, we have allowed all the transients to settle down, and then once you have settled down in the steady state, we are interested in knowing what is the gain that we have for such a system. But what does steady state mean? Steady state means that essentially, if you are looking at the number density, right, N2, how it changes with respect to time, what would that be? In steady state, that should be equal to 0, right, because there is no change happening. The pump level is held constant, and you are extracting a certain gain from this system. So, in steady state, that dN2 over dt should be equal to 0. So, let us write an expression for dN2 over dt. So, the rate at which you are pumping atoms to a higher energy level, right, where you are populating that energy level E2, what is the rate? R, right, that is the rate at which you are populating that excited state, and from that excited state you may lose some population to spontaneous emission, right. So, that is going to be given by N2 over tau 21, right. Since you are losing that number density, you have a minus sign corresponding to that, right. You may lose some population due to stimulated emission, and that rate is given by N2 multiplied by Wi, but you also have a way of gaining population, that is to stimulated absorption. What will be that rate? N1 times Wi. Do you understand how we are writing this rate equation? This is very important for the discussions that we are going to have as we move on. So, you just tracking the rate at which different events are happening. So, the question is, are we considering the inversion as constant? Yeah, this is, we are not actually doing this as a function of length yet. Okay. So, we are just looking at one particular location, and at that location, the atomic system that we have is having a 3 energy levels with these properties, and we are just trying to find out what is the inversion at that particular location. So, the length dependence does not come into the picture yet. So, of course, you can rewrite this and say N2 minus N1 multiplied by Wi is equal to R minus N2 over tau 21, right, where N2 minus N1, once again you can write it as N, which is what we want to find out, okay, So that is good. But on the right hand side you still have N2. Can we write N2 in terms of N and the total number of atoms? So the total number density, let's say, is Na. Okay. So if we say Na is equal to N1 plus N2 plus N3, but what can we say about N3? For this specific thing that we have considered, since it's short lived there, in steady state N3 is almost 0, right. So I can knock off N3 from this and then say Na equal to N1 plus N2. So from that perspective, if that's the case, then if you look at the inversion is given by N2 minus N1, and N1 can be written as Na minus N2. So this can be rewritten as 2 times N2 minus Na, right, and this would imply that if I can write N2 in terms of the inversion and Na. So N2 is nothing but 1/2 of N plus Na, right. So there is no magic in this, is just a straightforward expression. So the question is, what is Na? Na is the total number density of the dopants that we have. These dopants are the ones that are giving us gain, right. The dopants have these energy levels that we have mentioned here. Okay. So now I can substitute this into this other expression over here. So from here I can say that N into Wi is going to be equal to R minus 1 over 2 times tau to 1 multiplied by N plus Na, right. And so in this case we know tau to 1 for a given atomic system. Let us say we know what it's already been characterized, what is that spontaneous lifetime, right. So we know tau to 1 for a given atomic system. We also know what is the doping density, we know Na, and let us say we know what our pumping rate is, right. That just corresponds to how much what is the rate at which we are sending in pump photons. So if all those are known, then the only unknowns are N and Wi. So I can actually find out what is the expression of the inversion as a function of Wi. Okay. What is Wi now? That is the stimulated absorption or the stimulated emission rate, right. How is Wi expressed? We looked at it in the last lecture. What does Wi mean? That corresponds, what does it depend on? That corresponds to the flux density of photons that are coming in, and what else? The cross section, right, the absorption or emission cross section. Okay. So, Wi corresponds to that. So, essentially what I can do is I can now track inversion as a function of the flux density of photons that are coming in. And mind you, I am not talking about pump photons, because pump photons are separate. I am tracking that through R. What are the photons that I am talking about here? These correspond to the signal photons. Okay, the photons that needs to be amplified in the system. Okay, so I can just rewrite this, or maybe I can just carry this over, right. So from this I can say this implies that n, I can just rearrange some terms and say this will correspond to 2 times tau 21 R minus Na divided by 2 times tau 21 Wi plus 1, right. So what I am doing is all the factors corresponding to n I am taking to the left side, and the other terms I am retaining on the right side, and then just simplifying from there. So I get an expression like this. So this I can write as n equal to n naught divided by 1 plus some term tau s multiply by Wi, because I want to plot n as a function of Wi. So of course, where I can say where tau s would correspond to 2 times tau 21. Okay. So that's just a time scale that corresponds to 2 times tau 21, and tau 21 is actually the spontaneous lifetime from that particular energy level 2, and n naught is nothing but 2 times R into tau 21. I can write it as TSP. In fact, this one also I can write as TSP. TSP I am substituting instead of tau 21, but it's just saying it's a spontaneous lifetime, right. So, so n naught is given by 2 times R times TSP minus Na. Okay. But if I plot this, it actually gives me some a very important result that needs to be kept in mind, right. So n I am plotting as a function of Wi. How is that going to look? So of course, when Wi is 0, that is going to have the value of n naught, right, and then as you increase, it is going to go down, the value of n is going to go down, and it is going to take the specific value of n naught over 2 at what point? When do you get this? When Wi equals 1 over tau s, right. So at a particular value of Wi, it gets to n naught over 2, and just to emphasize, what does Wi indicate? Wi is given by 5 times sigma, right. So, sigma is the transition cross section and phi corresponds to the flux density of incoming signal photons, right. Now, sigma is a constant, right, for a given atomic system, that sigma is a constant, but phi is a variable, right. So, what does this graph tell us? This graph tells us that initially I do not have any signal photons coming in, but I am pumping, right, and so I am pumping and I am maintaining a certain inversion. What is that inversion? What does it correspond to? N naught, right. When Wi is 0, I have a certain inversion. That is what we are talking about, 80% of the inversion. I mean 80% of all the ions are sitting in the excited state. That was just an example. Normally it is not that high a number, okay, but nevertheless you have a certain inversion. But now I start sending in some signal photons that needs to be amplified. What does that do? According to this graph, that actually reduces the inversion that is available to you. Why? Because they have been depopulated, right. So, if you are getting amplification, right, and if you are actually sending in more and more photons, if you are sending, let us say 100 photons, and let us say they are all spread in time, the first few photons, let us say the first 10 photons comes and it sees N naught, okay, it sees this large inversion, most of the ions are in the excited state. So, it gets a lot of gain, but in that process what does it do? It depopulates that excited state, it goes to the ground state. So, for the remaining photons that are coming in, you do not have as much inversion available to you, right, unless of course you pump harder and replenish this thing, but that actually takes some finite time. So, immediately after an amplification happens, that inversion gets reduced. In other words, this is what we call as this leads to what is called as gain saturation, because reduced inversion means reduced gain. So, as you increase the incoming flux density of signal photons, you are reducing the gain that is available to you, okay. So, let's stop at this point, and this is actually a very important concept to understand, because as we go on to not just looking at amplifiers, but as we go on to looking at lasers also, we will keep revisiting this concept, okay. And this is what we have done for a 3-level system. Now, we will go on to consider a 4-level system and see how things could be different in that case, okay. So, that is what is coming up in the next lecture.